Hello, my name is Pavel. I'm an engineering manager in Google Cloud and Cloud AI platform. And today I'll talk about ML engineering with Kubeflow. So in this talk, I'll cover an overview of the Kubeflow project and its architecture. So we'll drill down a little more into the details of the Kubeflow pipelines as one of the Kubeflow component as a foundational for enabling the best practices in ML engineering with Kubernetes. We'll discuss the details of those of some of the best practices that we infer from prior work. And then we'll see how those ML engineering best practices are implemented with TensorFlow Extended, TFX, and then how they work in action on Kubeflow. And then I'll do a demo of the product. All right. So introduction to Kubeflow. So Kubeflow is a platform for building and deploying reliable and scalable ML systems on top of Kubernetes. Kubeflow is independent on any particular place where Kubernetes would run. As long as Kubernetes is deployed, Kubeflow is using the standard Kubernetes primitives to operate. Kubeflow is a collection of multiple projects that are contributed by multiple authors. It's an open source product. It's an open source project that is developed in open source. It has the components in the Kubeflow has multiple upstream components that they infer the work from. For example, a Kubeflow includes such components as TF job for orchestrating a distributed training of TensorFlow jobs. So that has a dependency on TensorFlow, which is also an open source project that is developed separately. Yet it is the dependency on that is taken with Kubeflow, and then the TF job operator is implemented in the Kubernetes native way. Some projects are originated and maintained mainly within Kubeflow, such as Kubeflow Pipelines, for example. You can learn more about Kubeflow on the kubeflow.org, and which has pointers to the source code on GitHub, and then documentation for getting started, for deploying that to different cloud providers. And then running examples, and it has some guidances of how to create your content and your workloads. Kubeflow is cloud independent, so it runs on Google Cloud as well as other clouds, as Azure and AWS and IBM Cloud. Some history of Kubeflow. Kubeflow was originally released in December of 2017, mainly with the Google contribution in it. And then it came with just a few basic components: integrated Jupyter Hub, TF job operator for running distributed job, and a way for deploying TF serving models into Kubernetes for inferencing. It has grown since then by adding additional individual applications to it, such as Argo orchestrator, Selden for model serving, PyTorch operators, and so on. And at that stage, probably throughout 2018, it remains to be a collection of those individual applications and individual components. So later on, and in late 2018 and early 2019, we have introduced ML pipelines and Kubeflow Pipelines project and the metadata project, which served as a connection fabric to connect all these applications into a consistent experiences. And in the later 2019 and 2020, leading to Kubeflow 1.0 release, the main improvements in the project went into hardening and then getting it ready for really reliable production deployments. So that's where the project is at right now. I believe right now it's actually have introduced an incremental version on top of 1.0 is 1.1, and then going towards 1.2 by adding even more functionalities. So what is particularly interesting and powerful about Kubeflow is the community of developers that are contributing to it, which are coming from a lot of various companies and individually. So Google remains as one of the biggest contributor to the Kubeflow, but it overall in aggregate it is not. Majority of the code is actually contributed by outside of Google, from outside of Google. So now let's talk a bit more about the Kubeflow pipelines. So one of the projects there. So, and I'll start with this, that it is typically the perception that for systems with ML, the most complex and then costly component is the ML code itself. That takes the most time to develop and build. But oftentimes, in the reality, all the surrounding infrastructure that is required to reliably deploy and run ML is actually constitute the majority of the engineering cost and the complexity in the infrastructure. Such things as data import, feature extraction, validation of data, resource management functionalities, model serving infrastructure, monitoring. All these are complex and large parts of the infrastructure that is needed, that are needed to build reliable and scalable ML systems. Kubeflow is mostly focused around those parts, and Kubeflow Pipelines is one of those key projects in there. So also typically the collection of processes and practices about building and integrating ML into developer workflow is called as MLOps. And then here it shows one of the actually advanced version of the MLOps where what's been developed in the experimentation and development phase is the entire pipeline that builds a model autonomously in production. And then how the Kubeflow actually fills in the gaps and fills in the components on that map. And then we'll talk about this in more details of how this Kubeflow components work with each other. So there are a few key pillars in building Kubeflow pipelines project. So the Kubeflow pipelines project is built around the authoring experience for creating reproducible and scalable workflows, and then operation experiences for deploying and debugging and tracking those workflows. So the authoring part stands on or starts off with components and the tools for creating and sharing those components and building the components based on previously built ones and reusing them. Then composing the components into pipelines that also can be shared, and they can be based on pre-built templates that are targeting to solve a particular problem in a particular ML problem in a given domain. Then an engine that serves as the foundation for running those pipelines at scale, which comes with the orchestration engine, scheduler, the tools for monitoring and debugging those workflows, and ML metadata for recording and tracking the execution and exploring the historical aspects of this. So here's a user interface snapshot of Kubeflow pipelines that shows a deployed workflow and the result of one of the highlighted component. And then we'll do a demo later in this talk where we will be able to look at that in more details. Here's a 10,000 feet view on the Kubeflow pipelines architecture. So there are several key parts to this. The first is that all of these components are Kubernetes native components. So they are built and packaged in a way that makes it easy to deploy and run them on any Kubernetes deployment that makes it cross environments, cross cloud, and available in different form factors where Kubernetes runs. So it is a collection of custom resources and custom application and local user tools. So one part of this is the SDK and tools, which are shown in the right upper corner here. So those are the tools that help the users to build components, build them into a shareable form, discover them, discover the metadata about them, bring them into the pipeline definition scripts, compose these pipelines, run them locally, validate them, and then compile them into an intermediate representation. So the intermediate representation is a compiled version of the pipeline, which resolves the dependencies between steps. And then that intermediate representation is handed to the pipeline API, which stores it and provides APIs for scheduling and running and creating the runs. So the runs are executed by the orchestrator, which interprets the pipeline definition and schedules Kubernetes pods for every step of the pipeline. And the metadata store with the metadata publisher / recorder, which watches the execution of the components, captures the input-output information about the steps, and stores them alongside with the lineage information about the the artifacts that are produced. And then we'll talk about that in the next few slides, what that metadata does. The components, each component in the pipeline is fully isolated from the rest of the components in the pipeline and other pipelines and the system itself. So this way, the user can compose the workflow from the steps that use different versions of frameworks, different libraries, different dependencies, and then run each step runs in a fairly isolated sandbox. The components can do processing locally inside the pods and then just use the computational resource of the node on which the pod is running, or can invoke external services for doing things like executing Dataflow job or Apache Beam job or a Spark job. Those jobs can be executed in the same cluster if there's a corresponding resource deployed, or it can be executed by another in another managed service that is provided by the cloud vendor. So as I mentioned, a pipeline in Kubeflow is a collection of containerized task implementations, which can use pre-built components or have a fully custom built containers. Each component is described with metadata that captures the input information, output information, alongside with the types for every input outputs. It's a specification of a directed cyclic graph that prescribes the dependencies of the step from one another. This graph can be constructed directly in YAML and in the intermediate representation, or using an easy-to-use SDK in Python, which we'll see some examples of. So ML engineering. ML engineering is an emerging discipline that are extending the software engineering and bringing the practices that matter a lot in building reliable ML systems. And then this isn't a comprehensive list by any means, but something that is inferred from practice. I'll mention a few key ones. The first to call out is the data, and then treating the data artifacts in ML systems the same way as one would treat code. Means that having the ways to test the data, having the ways to version the data, and validate the data against some predefined assertions and constraints, which is much harder than typically to do the validation of code, mainly because the validation of data requires a more statistical and weaker approach than exact comparison of the outputs of the test outputs. And another is models. Model is essentially a program that is automatically built by the training algorithm. And then validation of the models is just as important as validation of code, but the ways of validating the model is actually very different. And it's also more based on the statistical techniques. Another important and interesting part at the same time is it systems and tools that enables the users to build code that builds models as opposed to just building the models and then deploying the models. So the artifact that has been built by the developer or ML engineer in those cases is the pipeline or code that is deployed, which builds the model in production directly. That enables reproducibility, that enables continuous training, that enables adaptation of the model to new arriving data, which is different from the cases where the model itself is deployed to production, in which case it remains static and not adaptive to the changing environment and changing data. Composability is super important in these cases. Ability to compose various versions of framework, various versions of libraries, and then still connect them together, yet being able to version them independently. Ability to compose models, take a previously trained models and train it for changed or a new data set, and then therefore speed up the training and make it more comprehensive. ability to track lineage. In the ML world, the volume of various artifacts and the dependencies across them is very complex. And in order to more effectively debug such systems and reason about them, one needs to understand all the things that went into building a model or building a particular or creating a particular outcome. And that requires traversing the lineage of those dependencies. And then an infrastructure for ML engineering needs to provide this capability. And then can be a continuous learning, an ability to run the training code in production, training pipeline in production that is reacting on the data arriving or changing, as opposed to relying on any particular scheduled interval or a human trigger. So here's an example of a typical end-to-end machine learning system, which starts with a model, deploys that in production, and starts serving requests. It is trained from the data. So some code needs to be written to import the data. Some code needs to be written to train the model. Then some code needs to exist to infer the feature from this, and then validate the data, and then capture these results in the way that can be used in the feature validation, and in the feature themselves are affecting the results of the data analysis. So as the model is deployed and running in production, some code may need to exist to capture the data that is given to the model for prediction, process it, potentially label that data, and use it in the subsequent training cycles. So all of those require both data and code to be treated at the same level. And then here's an example of a pipeline that comes with TensorFlow extended TFX, which is deployable and runnable on Kubeflow, which has a lot of those components pre-built in a way that conforms to those best practices. And then here's a set of examples for scenarios that are taking advantage of the rich metadata and lineage tracking, such as ability to traverse the lineage graph, ability to start the training from previously trained models, compare models across different runs, and etc. So let's look at the Kubeflow pipelines and TFX in action. So here is, I'm going to switch my screen to a deployed cluster of the pipelines. Here's the user interface of the Kubeflow pipeline that shows a template, which is a non-configured template of a pipeline, which represents essentially that IR in the intermediate position in a graphical form. The Kubeflow pipelines are well integrated with the notebooks. Here I'm running just a standard Jupyter lab, which has a pipeline definition script. Pipeline definition script lists out all the components that I want to use in my pipeline, and then connects the input and outputs between them. So one note here is that the script does not define the topology explicitly. It defines instead a data dependency. For example, for my schema generation component that is expected to generate a schema for my data set, I take an input for the statistic generator. So I'm not telling the system that the schema gen has to run after. I'm just telling that it depends on the data that is produced by statistic generator. So that enables the execution engine to actually execute it smartly, and then execute some steps in parallel, some steps sequentially, some steps can run continuously. So as I define my pipeline with a command line utility or an SDK, I can compile it. into the intermediate representation and deploy it to my cluster. So as I deploy it and run it in my cluster, I have a few runs that I ran previously. It takes a few minutes to run, and then here is already an executed graph that I have. So here I can explore every step that I've executed. I can look at the operational logs and see exactly what happens during the execution. So in this case, the logs are not showing much because these steps have been already previously executed and the result been taken from cache. If I take the trainer, so the trainer actually did run this time, and then it actually shows me the full log. So a few words about the caching. So the execution engine is smart enough to understand that if the steps that are in the new pipeline run have already executed in the past, so they use exactly the same inputs that were previously used and the code did not change, there is a way to turn on the cache, and then in this case, the step that doesn't run, it just uses the output from the previous previously recorded run. So for every input and output of the steps are captured. So like in the case of schema generator, for example, I know that my schema generator have consumed the statistics and then produced the schema. And here is the URIs to actually fetch the underlying files. I can also look at the graphical representation of the schema, so components can produce a more rich visualization of their outputs. And then I can look at the metadata that has been generated and captured by the metadata recorder. So here I can find my model artifact, for example, and I can look at the lineage of that model artifact, which shows me where that model was used as it was built. So I can see that it was used in this particular evaluator and the pusher. The evaluator produced a blessing flag on that model, whether the model is blessed for deployment and the details of the evaluation. And the pusher used the model to push the model to production. So I can see where my model came from. I know that the model was built by the trainer, which used these 3 inputs. So this particular input, the schema, I can shift the focus of the viewer into the schema now from the model. And then the schema was generated by the schema gen. The schema gen actually ran twice on different runs, but the second run was taken from cache, and that's how I ended up with exactly the same schema instance. So and then so on. So this part of the Kubeflow pipelines allows me to navigate through the dependency graph in metadata. So this concludes my talk, and then I'll see you in the Q&A. Thank you very much.